I'm Lysa Posner, and today we're going to talk about whether fish can feel pain. So we're going to talk about nociception, which is the perception of pain in fish. So I want to start with what my nephews call my credibility factor. This is really for the audience to decide whether you should believe what I have to say or not at all. So my background is that I am a veterinarian. I am a veterinary anesthesiologist, which means I have advanced training in anesthesia and analgesia. And my primary research interests are anesthesia and analgesia in fish species. So that's my background. And then you can decide from there what you want to believe from what I say. So I get this question asked a lot. Do fish feel pain? And I think that it is still a controversial question. And I think that there's no easy black or white answer, like all of science. But so we're going to spend the next hour or so chatting about whether fish can feel pain. So this is a picture of my dad. This is not me. This happens to be one of my nieces. And my dad really thought you could judge people by how they treated animals. But my dad was also the one who taught me how to fish. And I remember being just about her age, and we're out at the shore edge fishing, and I remember asking him quite clearly, hey, you know, this seems kind of mean. Is this really an okay thing to do, this whole fishing thing? And he assured me quite clearly that fish can't feel pain or don't feel pain, and that this isn't really mean. They can sense that something's happened to them, but they don't feel pain, and we were cool with what we were doing. And you might just think that's some old coot's view of the world, and he was indeed an old coot. But if you look at some really prominent fish biologists or marine biologists, Dr. Rose is a professor out at the University of Wyoming. He quite clearly also believes, just like my dad did, that fish can't feel pain. And this is a quote from one of his papers, fairly recent paper, 2002. He has a more recent one where the verbiage is just about the same. And I'm not going to read the whole thing to you, but I want to point out that he says that fish are missing some of the higher cerebral structures that are required in order for them to feel pain. Therefore, they don't have pain, and they can't have fear. Even though, and I'm down at the last sentence now, they display a robust, non-conscious neuroendocrine and physiologic stress response. So what he's saying is that they respond, as you and I would, to a painful stimuli, but because they're missing some of the neuroanatomy, they can't actually feel pain. So my hope for the rest of our time together is to review the pain pathway as we understand it in mammals. That's where the vast majority of information has been evaluated. And then we're going to compare it to what the neuroanatomy that we understand and response that fish have, and see, at least from a scientific point of view, whether they have the neuroanatomy that would be necessary for them to feel pain. And my goal is not to try to convince you of anything. My goal is to give you the facts as we understand them and let you draw your own conclusions, which is what I always think you should be doing anyway. So for those of you who don't spend your lives studying pain as I do, there is an entire association, an international association for the study of pain that has a definition of what pain is. And so pain is an unpleasant, not a surprise, sensory and emotional. And I put the "and" in a different color because that's a pivotal point when we talk about the difference between just perceiving something that could cause damage and something that causes pain. So it's sensory and emotional, and it can be associated with actual or potential tissue damage. So it doesn't matter if I come over there and just step on your toe and don't actually hurt it, or if I take a scalpel blade to it and actually damage it. Both of those things can cause pain. And it has to be described in terms of such damage. And for a long time, only humans were considered able to feel pain. And researchers and physicians and veterinarians alike would say that animals didn't feel pain. They just had this nociception. But then there was a real discussion about whether nonverbal people, whether from disability or from age, newborns that were not able to express pain, were they still able to feel it? And the society went further and said that the inability to communicate doesn't necessarily mean that an individual isn't feeling pain. And then the doors kind of opened for everyone to start using the same words as long as they followed the same neuroanatomy pathway. So let's just get our verbiage straight. So nociception, the word that I started with, does not equal pain. Nociception is the process by which an organism or an individual detects something that is potentially damaging to it. Okay, so you don't need a brain to have nociception. You just have to be able to detect that, hey, this could damage my cells or this could damage my body. When we talk about nociceptors, these are receptors that sense that information that could and would lead to damage to tissue or an organism. Pain, the difference between nociception and pain is that pain includes the emotional component that comes from activating the higher brain center. So if you can perceive it, but you don't have a brain to make that into a complex emotional response, it's not considered pain. So we're going to talk about that because often that's here's a little foreshadowing, that's where a lot of the people who say fish don't feel pain is say that they don't have those higher brain centers in order to take it from nociception, which is exactly what my dad said. They know what's going on, but it doesn't actually hurt. So let's find out if that's true. So I think we need to find out whether that's true for a few reasons. First, so why do I care? First is that from a humane point of view, if fish can feel pain, we need to know that so we can treat them humanely. From my world as a veterinarian and a researcher, we talk about client satisfaction. So there are lots of fish that are kept as pets. There are lots of fish that are raised for food, and there are more fish now used as research models than any other species. So the zebrafish has taken over as the #1 research animal. So if we use fish in all of these ways, we have to if they do indeed feel pain, we have to make sure that we know that and be able to treat that appropriately. And then we have to think about the physiologic consequences. If they feel pain, just like every other animal that can feel pain, there are physiologic consequences to it. And that could be as simple as, hey, if you're in pain, you're not going to eat as well and grow as well. From a production point of view, that's real. But there's also potential for increased morbidity and mortality. So if you're doing research or you have the pet fish, the same consequences that I would worry about a dog in pain or my grandmother in pain, we need to know whether that's a reality or not. So let's go through the pain pathway. And like I said, we're going to do a little compare and contrast from what we know about mammals and see whether fish follow suit. So this is what we call a classic 3-chain model of nociceptive processing. So what that really means is that there are 3 neurons that are necessary in order for an external pain stimulus to get to the brain and have us perceive that as pain, right? So here is, in this diagram, this is from a Vet Clinics of North America. This is the foot or a paw of a rat or a dog or whatever you need to imagine in your head. Something activates it, and we it activates this first primary neuron, which goes up to the spinal cord. This structure here is the spinal cord. So this first neuron goes up to the dorsal horn of the spinal cord. From the dorsal horn of the spinal cord, it goes up to the thalamus. And then from the thalamus, it goes up to the cortex. And we're going to talk about that. So the stimulus that started here, let's say I stepped on that dog's foot, has to get all the way to the cortex in order for it to be perceived as pain. So I mentioned before that nociceptors are receptors that activate neurons that transmit this painful information. And you have to realize or appreciate that there are different things that can activate these nociceptors. So we can have mechanical information, so things like if I step on the foot, thermal, hot and cold, chemical, often these are acids, or electrical stimulation. And if you've not thought about this before, it probably makes sense to you that all of those feel different to you. They still all hurt, you go ouch, but they feel different. You burn yourself with a pan, feels different than if I step on your toe. And that's because you have activated different receptors, right? consequently, there are different receptors that sense those things. So we've got things like mechanoreceptors, we have temperature receptors, we have what are called silent receptors, which are activated mostly from chemical mediators. But and then there are some that will respond to more than one thing at the same time. So it's important to realize that there are different kinds, and they're going to be in different places. So just a little background on the nerves. We don't have time to go into too much of the nerve structure itself. But there are different types of nerves that transmit ascending, so going up towards the brain information. And the big differences are going to be their size and whether they're myelinated or not. So in this little diagram here, you can see these are what are called A-beta fibers. They're pretty big. And they are myelinated, which means the information travels fast. But these tend to not transmit information that we perceive as pain. These are more things like pressure and some proprioceptions. But they can be recruited in abnormal pain states. But the important part is that they're low threshold. So it doesn't take much. You can just come over here and touch my arm, and I'll know exactly where that is, because that A-beta fiber fired up and said, hey, you should feel that. So from there all the way to my spinal cord, to my brain, it says, hey, I noticed that, right? The two type of fibers that tend to, that are responsible for transmitting painful or noxious stimuli, the first one is the A-delta fiber, so it's smaller. It's also myelinated, so the information is very quick. And this transmits what we call the first pain. This is that sharp, really localized pain. So if I come over with a needle and I stick you, you know exactly where it is. You know almost the second I stick you, the information goes very quick to the brain and you can respond to it. The other type of fiber are what are called C fibers. These are even smaller, but they are not myelinated. So this information travels much more slowly, right? This transmits what we call secondary or slow pain. This tends to be that kind of burning, gnawing, miserable pain, and it's not quite as localized. Like, it tends to be more diffuse in its information. So those of you who have like cut yourself and you're like, oh, that doesn't hurt very, like really cut yourself with something sharp, and you notice it and you look down and you go, ow, but you're like, oh wow, that's going to hurt a lot more later. So that first ow was your A delta. But then when the other information comes on the C fibers, that's when that gets riled up, and your finger starts to throb, and it's more diffuse pain. So those are the fibers that transmit that information. And I belabor that. I stop and talk about this because we need to find out if only mammals have these, or if our fish species can transmit the same sort of information. All right. So when we talk about pain and nociception, I'm pretty much just going to call it pain from now on. There are 4 things that have to happen in order for you to perceive that something hurts you, right? And these are the 4 things that we talk about: transduction, transmission, modulation, and perception. We're going to go through each one, and we're going to see whether our fish species, are able to fulfill those things. And, I put at the bottom, is it pain when it becomes articulated? I don't think you need to be verbal in order to feel pain. And I think that most of our animal species have an emotional component. So, if you've ever stepped on a dog's foot, that's not just information, So I'm just going to call it pain from now on. So let's go through these 4 different things, talk about what they are, and talk about whether they have equivalence between our mammals and our fish species. So first we have to talk about where these nociceptors are, right? So make sure that we know where they are. So they tend to live in our superficial somatic. And what I mean by that, that's going to be your sub-Q and your skin and your mucous membranes. That's the very peripheral part. And it makes sense. You have all kinds of nociceptors. Just think about on your skin that can detect things that would result in actual or tissue damage. Then you have nociceptors that live deep within structures, so in your muscles, your tendons, your joint capsules. And then even more deeply, if we're going from the outside to inside, you have visceral nociceptors that live on things like your organs. Those tend to be what we call the silent. Remember, we call those C fibers. Day in and day out, you don't actually feel your intestines. Excuse me, if you cut them, you cut intestines, you don't feel that. But they certainly respond to stretch, so gas, gas. They respond to chemical mediators, acids. So there are, that's why it feels different when you have abdominal pain than if you have hurt your arm. All right, so let's talk about this first one. And I put these 4 in the corner so that you can always keep track of them. These might be new words for a lot of you. So the first is transduction. Okay, so transduction of a neuron. What that means is that you're going to take an external stimuli and transduce it. You're going to transform it into an action potential, which is what the nerves carry, right? So we're going to take some sort of information, and our nociceptors can perceive mechanical, chemical, electrical, and thermal information. So if I take a pin and I stick you on the arm, we're going to take that nociceptor is going to take that external information and transduce it into an electrical potential that then the nerve can carry. That's called transduction. So that's the way that we activate these A delta or C fibers. Okay. So what about transduction in fish? Right. So what do we know? So we know that fish have extensive nociceptors. These are the receptors that sense stimulation that you and I would call painful. And in this diagram here, you can see that there are 3 different shaped arrows. Like here's a triangle, and here is a diamond. Each one of those represents different types of nociceptors. And in this one project by Dr. Snedden, she looked at primarily the face. That doesn't mean that there aren't nociceptors in the rest of the fish. It means this is where this particular study looked at. And what they found is that fish have not only a wide variety, that they can sense many different types of information, but they are also widely distributed. There's lots of them sitting up here in the face. So fish absolutely have nociceptors. It's interesting to look at the phylogeny of nociception. So this is kind of a busy chart, but what you can see, what it does is it breaks down the types of species, from a phylogenetic point of view. So here are mammals up here at the top of the chain. Here are our bony fish, or a teleost fish. This is a rainbow trout. And then you keep going down, so things like lampreys, which are less evolved types of fish. And what the diagram shows is the type of nociceptors they have. So in the legend, you'll see they're myelinated or unmyelinated, and the types of things they respond to: mechanical, heat, chemical, and thermal, or cold, excuse me. So you can see that mammals respond to all of them. Okay, they have myelinated and unmyelinated. Interestingly, fish have myelinated and unmyelinated, bony fish. We're talking about things like trout. They respond to mechanical, heat, and chemical. They don't respond to cold quite so much. And then as you go down, so things like lampreys don't have myelinated fibers. So as you go down that evolutionary pathway, you will see that the more advanced animals, I'll call them advanced, have more ability to sense danger around them. But fish is really too big an umbrella, and most of the stuff I'm going to talk about today, we're going to talk about the bony fish. But I just want to point out, so our least evolved fish species, or our oldest fish species, are our lampreys. Probably you've seen them. These animals don't have myelinated fibers, so that means that information they get goes pretty slowly. But they do have mechanoreceptors, and they can sense temperature. Our elasmobranchs, these are things like sharks and rays, these are cartilaginous fish, have myelinated neurons, but they do not have myelinated nerves, but they don't have unmyelinated nerves. Our teleosts, like I said, our bony fish have both. So they have myelinated, unmyelinated, and respond to a variety of external information. All right. So we know that our bony fish, at least, they've got the nociceptors, and they can respond, they can activate sensory neurons, with electrical, chemical, thermal information. All right, our next piece is the transmission. Remember, transduction, transmission, modulation, perception. So let's talk about transmission, all right? So here, we're on the number 2 here. There has to be a way for that information, once it gets on that first order neuron, to then go all the way towards the higher brain sectors, right? So we're back to the original diagram that I showed you. So here's your first order neuron. That goes up into the spinal cord, and then from the spinal cord up from the thalamus, and from the thalamus to the cortex. Realizing that the destination, the final destination has got to be a higher brain center for there to be emotional component for there to then be pain. The difference between just sensing a stimuli and actually calling it pain. All right. So there's lots of stuff that goes on here in the dorsal horn of the spinal cord, and we'll talk a little more about that. But basically what's going to happen is that first order nerve is going to synapse there. It's going to go to a second order neuron that then is going to go up towards the higher brain centers. And then the third order goes from the thalamus, which is a lower brain center, to the cortex, which is a higher brain center. Like I said, the cortex is your target for perception. All right. So what do we have in fish, right? So this is the diagram that I showed you before. 3 nerves, one going to the spinal cord to thalamus, thalamus to cortex. So what do we have here? So if we replace this paw with the nociceptors that we know exist in the face of fish, so imagine a hooked fish, activate, it's got a primary neuron, it's got a secondary neuron from the spinal cord to the thalamus, and then it's got a third neuron that goes from the thalamus to the telencephalon. So realize here this is called the cortex. This is called the telencephalon, and we're going to talk later about whether that's the same thing or not. Okay, so clearly it's got a different name, but does it function in the same way? We'll come back to that. But from a neuroanatomy point of view, there is the ability to go from a peripheral nociceptor all the way up to the highest brain structure. So yes, they can transmit that information. The third piece is modulation. Can they take that information and modulate it? And you might not appreciate this, but your body does this all the time, right? And it's your spinal cord that actually modulates how much information goes up or down. I'm going to go back to this slide. This dorsal horn of the spinal cord here, in all of our animals, is what sometimes is referred to as the gate. It decides how much information goes up and down. And the best example I can give you of that is think about that first winter or fall day when you put on that wool sweater and you put it on and every nociceptor on your torso fires up and goes, wow, that's itchy. Your dorsal horn decides, hey, I'm going to either keep sending that information up to the brain, and then you'll probably just take that sweater off, or the dorsal horn says, wow, I need to stop sending that information. It's not really useful. I'm going to just stop sending that. So your body does this all the time. Your body also does this all the time in response to injury. And that modulation occurs at all different levels. So your highest brain center, your cortical and thalamic areas can control your endogenous opioid system. So those of you who are serious runners and love your runner's high, that's what happens. You kind of injure yourself enough that your brain sets off and allows the release of endorphins that then make you feel better. But that's a way of you self-modulating your pain. Your spinal cord, we already talked about, they can decide whether to continue to send information or not. It's got all kinds of cool neurotransmitters in it. And then there are local effects that can occur peripherally, right? So what do we know? What do we know about fish and modulation? So we know that they're dorsal horn gates, just like mammals do. We know that they have a descending modulatory pathway. This to me is incredibly important because it makes no sense from an evolutionary point of view to waste all of those resources on creating things like opioids and opioid receptors if you don't need to modulate pain. If this is just information, if it doesn't hurt, then there's no reason to create those receptors and create the opioids. We know that fish have both at least two types of opioid receptors, the mu and the kappa. They have the ligands that bind there. They also have alpha-2 receptors, which are commonly found together in mammals, the opioids and the alpha-2s in the dorsal horn of the spinal cord, and they have ligands that bind there. So fish have a pretty extensive way to modulate pain, which again, for me, just being critical, it doesn't make sense to have that if you're not trying to make pain rather than nociception go away. Fish also have a pretty extensive inflammatory pathway that is blocked by nonsteroidals. So they have a pretty sophisticated system. There is a great deal of research that goes on in zebrafish because the opioid receptors in fish and the opioid receptors in humans are incredibly similar. So fish indeed can modulate, so we're going to give them a check there too. So perception is where a lot of people draw the line. They say, okay, this is great, we've got all this neuroanatomy, I agree with all of it, but if you don't have a cortex, and we don't call the higher brain centers in fish a cortex, then they can't possibly be feeling pain. And we have to critically think about what we're saying when we say that. So, as I said before, this higher brain center is where pain gets perceived. So everything else is just information till it gets to that higher brain center that perceives it as unpleasant. So what do we know about that in fish? So let's review the brain and see if we can't draw or look at some facts and decide what we think about them. So this is a diagram of the embryonic vertebrate brain. Okay, so what that really means is we're talking about vertebrates, so anything that's bony, and that includes, so that's you, me, and fish, and everything in between. The embryonic brain looks pretty similar across the species. So my brain, fish brain, we pretty much all started the same way. So here's your spinal cord, here's the hindbrain, here's the midbrain, and this is the forebrain. And as an embryo, it's called the telencephalon. Okay, it's got other parts to it too, but the highest brain center is considered the telencephalon. As that develops from an embryo to a living animal, you can see that the human brain forms into the structure that we're pretty comfortable and that we see, and that this becomes a big cortex, and the cortex is surrounded by a neocortex, right? You can see that the fish brain does not develop the same way. So we still have, so here is your brainstem, here's your thalamus, here's your higher brain center. In your fish, here's your brainstem, and then you can't see the thalamus here, but here's your cerebellum, and up here, the highest brain center is the telencephalon, clearly much smaller, less defined, and only mammals have a neocortex, right? So birds, fish, reptiles do not have a neocortex. The neocortex has been, that line in the sand for a lot of anatomists and evolutionary biologists to talk about. The neocortex is associated with language and is associated with problem solving. And for many years, that was the line in the sand. They would say any animal that does not have a neocortex can't have language and can't have higher brain problem solving functions. And I think that just over time and study and some logic will make you realize that that's really not a fair line in the sand to have. And I say that because we know that there are lots of birds that communicate through song. And now, whether you want to call that language as we know it, I think I would. If you're communicating and you're using sound to do it, I would call that language. And we also know that there are lots of species like birds and even octopus who do all kinds of incredibly sophisticated problem solving. They don't have a neocortex, so I don't think that means that they have the ability to problem solve or not. But you will hear some people say that that's a line in the sand, this neocortex here. So what do we know? We know that the telencephalon in fish, so this highest brain center, albeit pretty small, is active during nociception. And the way we know that is that if you stick a fish with a needle while it's in a functional MRI, this part is the part that lights up. So that information from that peripheral pain response all the way to the highest brain center is activated, right? So we know the telencephalon is activated. And as I've already said, I don't buy the answer that the neocortex is the line in the sand. It just doesn't make sense to me that only a neocortex would be actually involved in the pain pathway at all. Perhaps the expression of it, but not in the pain pathway. Fish also have this crazy olfactory system, very complex. There's a lot of stuff we don't know about it yet. And it clearly is involved with olfaction. So it is involved with food, finding food and hunting for food. But what they've recently realized is that it does lots of other things, and it is involved with social interactions and being able to school and being able to mate. And so there may actually be some higher brain function that goes on in the olfactory system. We just don't know the answer to that yet. When you look at the brain processing, where the information goes, so here's a human brain, so we're back to the mammal. Spinal cord to the brainstem, right? Showed you that. That to the thalamus, and then thalamus to the cortex. If you look at the fish brain, you're going to have pretty much the same order of information. So from the spinal cord through the brainstem to the thalamus, and then from the thalamus up to this telencephalon, right? And then in both the mammals and in the fish, there's all this other stuff that then affects that processing, but there is direct information to the highest brain center. Whether you call it a cortex or whether you call it a telencephalon, it's getting to the highest brain center. So I don't think, honestly, that that's controversial, although for some of you this might be new information. But once you see this, it's not hard to make the jump. Well, okay, we've got the neuroanatomy, you pinch a fin, you pull a hook out of a fish, that information goes to the highest brain center. Then we have to decide whether that information that it gets there is actually painful perception. And clearly we can't ask them. And it's been interesting over the course of my career as a veterinarian to see how we as humans have decided whether we agree things feel pain or not. So when I was a student, there was the very beginning of, yeah, dogs and cats probably feel pain, but I remember professors telling me that they don't feel it like us. Like they're just, it's really just more information to them. And then as my career went on, and as we did more study, and as we started to be more rational about it, they're like, well, of course dogs and cats feel pain. But then there was horses didn't feel pain. And then, well, okay, now they do. And then there was, birds don't feel pain. And now the, accepted convention is they do. Then we moved on to reptiles. Actually, if you go back 50 or 60 years, they used to just say adults could feel pain, children couldn't. We keep realizing that we are putting that line in the sand way too soon. But there's a big difference between having the neuroanatomy getting to the brain and then having that be an unpleasant stimuli. So what evidence do we have that fish actually respond to this in an adverse way, right? And we have a few. So the first is that there are a fair number of studies that have looked at avoidance behavior in fish. And what's fascinating is that they have found that fish make conscious decisions about how much pain they will tolerate based on what the reward is. So fish that are normally happier in a school of fish, if you take one of them and separate them, that is incredibly stressful for that fish. And they will do lots of things to get back to the school. So in some of these experiments, they're actually able to electrify portions of a water column. So they put a school of fish on one side, they put electrical activity in the middle of it, and they put this one lone, sad, I want to be with the rest of my peeps fish all the way to the other side. That fish will make decisions based on the electrical current. So it will go through the painful stimuli to get back to its friends, up to a point, and then it will say it's not worth it. There's similar things have been done looking at food, whether they will, how hungry they are and whether they will cross a painful stimulus for food. It's not hard to teach a fish that in a certain area of its tank there's going to be a negative stimuli. They will stay away from it. They make those conscious choices. Fish also do this, what I call very interesting self-soothing behavior. So in one series of experiments, they inject acetic acid into the lips of fish. It's a fairly short-term painful stimuli. And then they observe either their response to analgesics or they look at their response to the painful stimuli. And what they found in these series of experiments that if they put the inject the acetic acid into the lips, the fish would go to the bottom of the tank and rub their lips on the gravel. Not much different than when you get hit and you rub that place that hits, right? Every toddler knows how to do that. We don't teach them that. And basically what you're doing when you do that is you're confusing the information in the dorsal horn of the spinal cord, so what gets up to the brain is attenuated a little bit. But fish do that. Fish, when they're in pain, will also rock. Interestingly, they will rock side to side. Most mammals, most humans rock forward, right? Ow, that hurts, ow, that hurts, ow, that hurts. They rock side to side. And what was interesting is all of those behaviors were attenuated, were decreased or even stopped when those fish were administered analgesics, things like morphine. So if you give a fish morphine and then inject it with an acid, it will act more normal. It won't rock, it won't rub, it'll do all of its normal stuff compared with ones that you don't give analgesics to. So that also raises my suspicion that they feel pain just like you and I do. Fish also lose their normal sense of their normal behaviors. They behave abnormally just like pretty much all the other animals do when they are in pain. So if you have a fish and you do surgery on it and you don't provide it analgesics, they swim less, they feed less. They also sometimes will change their height in a water column. So appreciate that fish live at different heights in the water column. Some are bottom, some are top. When they're in pain, they will change their position in the water column. And when the pain is either over, they've healed, or we've provided them with some analgesics, things like morphine or non-steroidals, they will then go back to their more normal behavior. They also have the same physiologic responses that we do to painful stimuli. Heart rate goes up. We call it a respiratory rate, but really we're talking that their opercular rate. Their stress hormones go up, things like cortisol. Now, granted, these aren't just specific. You can make a fish heart rate go up just by chasing it around the tank. But it is interesting that their physiologic responses are pretty much the same as ours in response to noxious stimuli. So if you put this all together, if you look at their neuroanatomy, if you look at their behavior, if you look at their physiologic responses, I think there's no question that fish feel pain. Do they feel it like you and I? I have no idea. But I also cannot, in good conscience, go, oh, they just don't feel anything at all. There's no evidence to support that. The only evidence we have of that is that it makes people feel better when they do mean stuff to fish. So we have to at least be critical scientists and think about that. So you could quote me and say that, yes, fish feel pain. Interestingly, there was an entire manuscript, there was an entire journal from the Laboratory Animal Resources group. They dedicated an entire issue to pain and distress in fish. They did not dedicate the issue saying, hey, do you think fish feel pain? They just went out and said they do, and what can we do to stop that or attenuate that? I was really flattered when they asked me to write the introduction on that, but they had a captive audience in me to start. So that's my coverage of the neuroanatomy of the pain pathway in fish. And I hope that you at least come away thinking about what we've talked about and then make your own decisions on whether you think fish do or do not feel pain, and then decide what you think is appropriate for fish care. And I thank you for your attention.